You all right, guys? I'm back. Time for some chemistry. So it's all about covalent bonding. Covalent bonding is one of the 3 types of bonding you need to know about. We need to know about ionic, covalent, and metallic. So that's basically what you go through in the bonding topic. Covalent bonding is by far like the biggest part of it. So that's why I chose to have a lesson on covalent bonding, because it's not just about the bonding. We need to know about the different compounds you can have, the different type of covalent compounds you can have, and also all the allotropes you can have of carbon. There's like, how much is it? 5 or 6 that you need to know. So we'll go through all of that. But we'll start off with the basics of what covalent bonding is. So it's all about electrons being shared. So you can see quite a few spec points here to cover. But yeah, first thing is, what type of compounds does covalent bonding occur between? What do you guys think? So ionic is between a metal and a non-metal. It's metal plus non-metal. Metallic is obviously between metals, between 2 metals. Thank you, Militia. Covalent is just between non-metals. So it's between a metal, non-metal and another non-metal. And what happens is you got electrons being shared between the different atoms. So it involves atoms sharing pairs of electrons so that the atoms can achieve a full outer shell. Full outer shell and become stable. That is always the aim here when it comes to bonding. With ionic bonding is the same thing. They always want to get a full outer shell because it makes them more stable. For ionic bonding, they transfer electrons, but for covalent bonding, they share electrons. That's the main difference between the two. So the reason why these bonds form, so let's see if we've got a diagram here. Yeah, we've got a diagram here. So you guys see this hydrogen here. We've got a hydrogen nucleus, and then in between, we've got some shared electrons. And what happens is those shared electrons are attracted. So you guys see these red arrows here. So this shared electron, remember electrons are negatively charged, it gets attracted to the nuclei of the 2 atoms. So the two atoms either side of it. That attraction is what holds everything together. That's basically the bond. So the attraction between here and the attraction between there. So these bonds form because the positively charged nuclei are attracted to the shared pair of electrons. Anyone know the name of this? I wrote it down. I showed you it already, didn't I? The shared pair of electrons by electrostatic forces. By electrostatic forces. Okay. So there's different types of ways to show covalent bonding using these different diagrams. Okay, so this one here is a dot and cross diagram. That's what I've drawn. Here is a dot and cross diagram where you basically represent electrons with dot from one atom and a cross from another atom. So these 2 are the nuclei. So that's one hydrogen nucleus, that's another hydrogen nucleus. And up above, we've got the shared electron. the shared electron. Okay. The one on the right is it's a much more simplified diagram. That is a displayed formula. We call that a displayed formula. And it basically represents the bond, the covalent bond, instead of it being two overlapping rings, it just is represented with a line. It's much easier to draw um, these types of structures with a displayed formula. But the problem with that is that it doesn't show the electrons, whereas the one on the left does show the electrons. So there's different advantages and disadvantages to using different types of diagrams. So this diagram is only used only needs to show the outer shell, because you can have up to 4 shells for GCSEs. In a covalent bonding diagram, you only need to show the outer shell. And it basically represents atoms sharing electrons with the overlapping shells. So wherever they overlap, so in between the overlapping sections, that's where the shared electrons are. So to represent atoms sharing electrons, this we'll say this type of these diagrams. That's probably better English. These diagrams have overlapping shells. Overlapping shells where the shared electrons are drawn. Displayed formula. So we see that quite a lot in organic chemistry. This uses lines to represent bonds. So it uses lines to represent covalent bonds. So every line you have is basically a covalent bond. And you can see here at the dot and cross diagram and displayed formula for different types of covalent molecules. So is there a list of ones you need to know? That's what I'm trying to check here. So I'm trying to look for the most common ones. I'm just seeing if it's in the spec. Can't seem to see them, but those are like the most common ones that come up. But yeah, anyway, we've got a few examples here: hydrogen, chlorine, oxygen, nitrogen. Okay, hydrogen only has one electron, so they share that one to give it a full outer shell of 2, because remember the first shell can only hold 2 electrons. Then we got chlorine. Chlorine has 7 electrons on its outer shell, so they need to share 1 to make a full shell of 8. That's why this one has 7 here. So 7 dots, 7 crosses, but you share one dot and 1 cross to give 8 to each one. And both of these have single bonds between them. So every pair of electrons you have corresponds to 1 covalent bond. So now if you look at oxygen, look at how much is in the middle. We've got 4 in the middle. So that's 2 pairs. So that's a double bond. Then if we look at nitrogen, that's 3 pairs. There's 6 electrons in the middle. So that means it's a triple bond. Okay, so each pair corresponds to 1 covalent bond. Single bond, double bond, and nitrogen's a triple bond. I don't think you'll come across another triple bond in GCSEs. So it's all good. All right, we got a few more examples. We're going to draw the displayed formulas for this. So all of these seem to have single bonds, right? So you can see here, hydrogen and the chloride only has one pair between it, so we would draw this like that. Then we've got water, so the next one is H2O. So that's going to be H bonded to O, bonded to H. Next, we've got ammonia, which is N bonded to 3 H's. And then we've got methane, which is carbon bonded to 4 different H's. All of these have single bonds. Right? So let's look at a few other types of diagrams that you can have. So we've talked about dot and cross diagrams, and we've talked about displayed formulas. In an exam, you might also see a 3D model diagram. So you won't get asked to draw one of these because they're 3D, so it's way too hard to draw for an exam. But I've seen questions where they show you one and they ask you to figure out the molecular formula of this. So these are good because they allow you to see how the 3D arrangement of the molecule is. Whereas the other two you guys see here, you can't really see the 3D structure. So this here is basically ammonia. This is NH3. All right. So compare this diagram to these two. This is ammonia here. So what you can see the difference is these two don't show the 3D structure of how ammonia actually looks like. So that's a disadvantage. But they also have advantages. Dot and cross diagram shows you the electrons. Disadvantage of a dot and cross diagram is too complicated. Then you got displayed formula. It's much simpler, but it doesn't show you electrons and it doesn't show you the 3D arrangement. These ones do show you the 3D arrangement. What do you think some disadvantages of these would be? Let me know in the chat. I'll fill in these atoms. What do you think a disadvantage of having a 3D model diagram is? So this is a nitrogen atom, and this is a hydrogen atom. And if you want to determine the molecular formula, no one knows? Molecular formula of a compound, count the number of each type of atom present. As there are, so here we've got 1 nitrogen atom and 3 hydrogen atoms. The molecular formula of this is NH3. All right. So no one knows the advantages and disadvantages of this. Okay, so this is what the next part is all about. So advantages of a dot and cross diagram. It shows electrons. So we know exactly where the electrons come from. This basically, the reason we're going through this, guys, is because they do ask this in your exams. Yeah. So it shows electrons. A ball and stick model. So the 3D model I showed you was it shows the 3D arrangement of atoms. None of the other ones do. And then the displayed formula, advantage of that is it's very simple to draw. That's why we use it in organic chemistry. Very simple to draw. Disadvantages, dot and cross diagram. It doesn't show the 3D arrangement. So you can't actually see how this molecule looks like in real life. That is not how it looks like. This is how it looks like, isn't it? 3D model doesn't show electrons. So you don't know how many electrons are being shared for each one. And displayed formula, again, doesn't show 3D arrangement. Doesn't show the 3D arrangement. What does it say in the second box? You're talking about this one? Shows the 3D arrangement of atoms. Or is it this second box? Let me say all of it. So shows electrons, no 3D arrangement. Shows 3D arrangement of atoms. Doesn't show electrons. Very simple to draw. Doesn't show 3D arrangement. Yeah? Okay, so yeah, you might get questions on this asking you to write the advantages and disadvantages. Okay, let's move on. So we talked about what covalent bonding is, how it occurs. Let's talk about the actual covalent compounds that you can come across. You can come across 3 different types of covalent compounds. So there are 3 types of substances made out of covalent bonds. First one is simple molecular. Second one is giant covalent. And the third one is a polymer. So we'll talk about all 3 of these now. And how to identify which one's which. So first one we'll go through is simple molecular. So simple molecular, it's basically in the name. So it's made up of molecules which are formed by, remember it's a covalent compound. So it's formed by covalent bonds. And within a simple molecular substance, this is where people get confused. Within a simple molecular substance, there are 2 bonds involved. Okay. So I always see people getting confused between intermolecular forces, electrostatic forces. Okay. Electrostatic forces we talked about already. That's between the shared electrons and the nucleus. We're not going to talk about that now. Electrostatic is when you have something positively charged attracted to something negatively charged. Okay? Electrostatic. We're not dealing with electrostatic here. Okay? What we're dealing with are covalent bonds, basic covalent bonds, and intermolecular forces. So we've already talked about what covalent bonds are. So they are, they form between atoms which share electrons. Intermolecular forces, they're different. The word intermolecular basically gives you a bit of a clue. These are forces between molecules. So not between atoms, they're between molecules. Anyone know the difference between a molecule and an atom? What's a molecule? What would you define as a molecule? So molecules, and we can say they're weaker. Anyone know what a molecule is? These ones are stronger. So molecule is when you have one or more atom bonded together. One or more atoms, 2 or more atoms, sorry, not one or more, 2 or more atoms bonded together. So you know all of the ones that I listed out here, all of these are molecules. So that's a molecule. All of this together is a molecule of hydrogen. This is an atom of hydrogen, but two of them bonded together as a molecule. This is an atom of chlorine. That's another atom of chlorine, but together they make a molecule. Okay? And molecules have intermolecular forces between them. So here we've got a chlorine molecule, or two chlorine molecules. These are diatomic molecules, Cl2. And within this molecule, see, can you guys see this? The orange part, that's an atom. So all of this is an atom. That's another atom, but together, this is the blue part. Together, they make a molecule. All right, so that's the difference. And can you guys see here? We've got two different types of bonds. We've got this purple bond here, and then we've got this dashed green bond. Those are the two different bonds that I'm talking about here. So the purple one is the covalent bond. And the green one is the intermolecular force. The intermolecular force. Okay, so remember that. Covalent bond is between atoms. Intermolecular is between molecules. So why is this important? Because they can ask you about melting and boiling points of these substances. So this is where people get confused. When you're melting or boiling something, what are you trying to do? You're trying to break down the forces. You're trying to break some forces, break some bonds. Yeah, because in a solid, they're all fixed and they're all held together by bonds. You want to break those bonds. Now, the question is, because we're dealing with two different bonds here, covalent bonds and intermolecular forces, which of these bonds need to be broken when you melt something like chlorine? Does anyone know? When melting something like this, which bond are you trying to break? Are you trying to break the intermolecular force or the covalent bond? It's one of them. And remember, one of them's strong, the other one's weak. So this one is strong. Let me know what you guys think the answer is. This one's weak. When you're breaking the bond of a simple molecular substance to boil it, which bond are you breaking? So Andrew says intermolecular force, and Indigens also says intermolecular force. Exactly, yeah. Intermolecular force is the one that you're trying to break. That is the weaker one. So because those are weaker, they need less energy to break, which is good. Because they're easy to melt. If it was the covalent bond, that'd be much harder to break, but we're not trying to break those. So that's what this is all about. So when simple molecular substances melt or boil, it is the intermolecular forces that need to be broken, not the covalent bond. Don't get that wrong in an exam, okay? And what do we say? We said these intermolecular forces are weak, meaning that only a small amount of energy or low amount of energy is needed to overcome them. So to actually break these weak intermolecular forces, you only need a low amount of energy to break it. This gives simple molecular substances low melting and boiling points. This is why they're usually found as liquids or gases at room temperature. Yeah, so room temperature is around 25 degrees. Yeah, 20 to 25 degrees. So that means if you have one of these substances at room temperature, because the melting temperature is low, they've already melted or boiled by that point. So that means they're either liquid or gas. They're rarely solids at room temperature. So if we look at our list here, hydrogen, that's a gas, 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 liquid, liquid slash gas, gas. Yeah, exactly. So they're not much, they're not solid as much. So yeah, all of these covalent diagrams, they are all examples of simple molecular substances. So remember, there's 3 types. So we're basically going through this right now, simple molecular substances. And they have low boiling and melting points. The other thing is when you're comparing different boiling points. So you see here, we've got 2 things that we're comparing. We're comparing chlorine, which is CO2, and iodine, which is I2. Both of these are simple molecular substances, okay? They both have boiling points, which are, or melting points, which are relatively low, okay? But one is much lower than the other. So what you can see here is that chlorine is minus 34, whereas iodine is 184 degrees, okay? But they're both simple molecular substances. The reason why is because iodine is bigger than chlorine. So these ones have weak, very weak intermolecular forces, whereas iodine has slightly stronger intermolecular forces. Okay, so because the iodine ones are stronger, they're going to require more energy to overcome. Okay, so what I want you guys to remember is the bigger the molecule is, the more electrons they have, so the stronger the intermolecular force. So what we're going to write here, we're going to say iodine atoms are larger. Why are they larger? Because you're going to find them further down the periodic table. So that means iodine molecules, remember the difference between atoms and molecules, have more electrons. So this means there are stronger intermolecular forces between the molecules. So that means more energy is required to overcome these forces, which means iodine has a higher melting and boiling point than chlorine. Hope that makes sense, guys. Let me know if there's anything you want me to re-explain. Okay, so we're done with simple molecular. Giant covalent. So the main difference between simple molecular and giant covalent is that in giant covalent, you're not really worried about intermolecular forces. Yeah, so no intermolecular force, no IMF involved here. What are giant covalent structures? So the word giant, the reason why we use the word giant is because there is really large network of covalent bonds. So you see here, this is an example. This is silicon dioxide. This is just a part of silicon dioxide. This structure keeps on going. So it makes like a huge like web. Silicon dioxide is basically sand, guys. So 1 grain of sand basically has this, but like 1,000 times. And that's all 1 particle of sand. So you don't have tiny, tiny molecules here like you do for the other stuff. You have one huge network of these atoms and covalent bonds. So you guys can see here, these are silicon atoms because of silicon dioxide. We've got oxygen atoms. And in between them, we've got the covalent bonds. So remember what I said. When you compare covalent bonds and simple molecular substances, I said that covalent bonds are strong, intermolecular forces are weak. All right. Here, we're only trying to break the intermolecular forces to melt them. Okay. But the problem with, not the problem, but the thing with giant covalent structures is that every single atom is connected with these strong covalent bonds. Every single atom, if you look at this, every single atom is connected with these strong bonds. So if they're all connected with these strong bonds, it's very difficult to break them. Very difficult to break them up. That means they're very difficult to melt, and they're generally solid at room temperature. Okay, so let's fill some of these in. These are structures where atoms are bonded in a large network of covalent bonds. Every single atom in these substances is bonded to another with strong covalent bonds. Like I said, they have high melting and boiling points. They have high melting and boiling points because a large amount of energy is required to break these strong covalent bonds. So the examples, so these two we're going to see in a second, diamond and graphite, they're allotropes of carbon. Silicon dioxide is another one you're expected to know. That's another giant covalent structure. Okay, and that's the one that we've got on the left-hand side here. So yeah, we'll visit these in a second when we go through the allotropes of carbon. But then let's just look at the last type of covalent structure we can have, which is a polymer. So polymers, you can think of polymers as they're molecular substances, but the molecules are humongous. Okay, so they're really, really, really long molecules. So they're like these long chains of molecules. We come across them in organic chemistry as well. But it is really, really long chains of molecules. So remember what I said? I said back here, I said the bigger the molecule is, the stronger the intermolecular force and the higher the boiling point. So compared to simple molecular substances, do you think polymers have high boiling points or low boiling points? So they're basically long molecules, right? So they're very long molecules. Do you think they have high boiling points or low boiling points? So Ninogen says low. They're very long molecules. So that means they have very strong intermolecular forces. So that means they have high melting and boiling points. Exactly. It's high. Okay. So these individual parts here, that's what this box is meant to be, but I'm just going to label it here. These are called monomers. Loads of monomers joined together to form polymers. high melting boiling points. I wrote that there. Okay, so here we'll write strong intermolecular forces. So compared to covalent bonds, they're weak. Intermolecular forces are weak compared to covalent bonds, but relative to other molecular substances, these ones are very strong. So we're going to say they're strong intermolecular forces. So polymers, these are chains of repeating units known as monomers. These atoms within the chains are held together by covalent bonds, which create large, so creating large molecules. What are those squiggly lines on the side? These are loads of polymer chains. Well, they're meant to be. I need to draw that. I was just trying to show you how these look like from far away. So imagine these are the squiggly lines, these polymer chains. You've basically got loads of these. They're huge molecules, and they've got really strong intermolecular forces holding them together. Yeah, but you don't need to draw that. So what are they? These are long-chained molecules. So we'll say these long-chained molecules are very large. That's the key thing about them. They're very large. So they have very strong molecular forces, which require a lot of energy to overcome. This results in polymers having high melting and boiling points, which means these are usually solid at room temperature. Okay. When you think polymers, think plastics. Yeah, so they're plastics. Another way to represent polymers is like this with square brackets. Okay, so what this basically shows you is, so this is a displayed formula. It's a much more simpler way of drawing them. Imagine this repeating itself several times. So imagine that copying itself over and over again, several times. That's basically what a polymer is. So what we need to do to show the displayed formula, we want to simplify that as much as possible. So what we do is we just literally just show one section of it. That's a repeating unit. We're basically showing that this is repeating, all of this is repeating n times. N is just a number. It could be 1,000 times. It could be 10 times. It could even be 2 times. But it's a number that we don't know. But it's repeating that many times. When did the Easter boot camp start? So over Easter, I'll tell you guys the exact dates next week, or we'll send across an email. We're gonna have a few sessions, like quite a few hours, full day sessions, basically, where we're gonna go through everything you need to know. Yeah, but we'll send you details of that. Send you details of that soon. If you guys are part of the part of this subscription, then yeah, you guys will be able to join easily. But we'll let you know. We'll let you know when it is. So this shows the repeating unit. Remember I said the repeating unit? That's of the polymer. So this one's called polyethene, and the structure within the bracket is repeated several times to give the structure of the polymer. So that's just a way of showing how the polymers look like. Okay, let's go through the allotropes of carbon. So first of all, let's explain what an allotrope is. Don't get them mixed up with isotopes. Allotropes are same element, different structural form. Okay, so different structural forms of the same element in the same physical state. Okay, so for carbon, there's a few that you need to know about. This one here is diamond. You need to be able to recognize these. So we've got diamond, we've got this 1, 2, 3, 4, 5 different ones that you need to know about. So what do you need to know about diamond? You need to be able to recognize it. Do you guys recognize that this is similar to silicon, the one I showed you earlier, silicon dioxide? They both have the same shape. Call it a tetrahedral shape. So they're formed from carbon atoms, each sharing 4 covalent bonds. Okay, so that every carbon atom here is bonded to 4 other carbon atoms. So as a covalent diagram, dot and cross diagram, this is how it's going to look like. That's one. That's bonded to another. Third one. And a fourth one. Okay. Carbon has 4 electrons on its outer shell. 1, 2, 3, 4. So it's basically sharing electrons with 4 other carbons around it. That's what's giving it this structure. All right. Remember that because we're going to come back to that for graphite. Diamond is very hard with a high melting point. That's because, remember what I said about giant covalent structures. Every single carbon atom is held together by covalent bonds. Yeah, it's a large network of covalent bonds. So it's because of the large network. That's a key term there. Of covalent bonds that require a large amount of energy to overcome. It doesn't conduct electricity. For something to conduct electricity, it needs to have free moving ions or electrons. This one doesn't, as it has no free moving ions / electrons. You've never heard of, you've never heard of? You've never heard of diamonds? Or are you talking about silicon dioxide? Sorry, I mean diamond in chemistry, obviously. You've next one is called graphite. Of course, not diamonds. So which one have you not heard of? You mean silicon dioxide? Allotropes. You've never heard of allotropes? Okay. Well, at least you know it now. That's in the spec. Yeah. Okay. So graphite. So what's the difference? A graphite, can you guys see the structure here? It's a hexagonal structure. And it's not just normal hexagonal. Hexagonal. What am I supposed to? Composed of layered of hexagonal. Sorry. Rings, each with each carbon bonded to 3 other carbons. And the other thing about it is it exists in layers. 1 layer, 2 layer. Okay? So it's composed of layered structures of hexagonal rings with each carbon bonded to 3 other carbons with covalent bonds. Its carbon has 4 electrons on its outer shell. So the 4th electron is not used for bonding. Okay, so let me explain what this means. So remember I said I'll come back to this diagram. So in diamond, we've got each carbon bonded to 1, 2, 3, 4 other carbons. Yeah, that's how we get this structure, tetrahedral. Here in graphite, can you guys see each carbon's bonded to 3 other carbons? 1, 2, 3, hexagonal ring. So that means because it means one of its electrons are not being used because it's only bonding to 3 other carbons. So it's got 1 spare electron here. Do you guys know what that does? This delocalized electron. Why is that unique? So 1 electron's not being used in bonding, so that one's free to move. So what is that going to mean in terms of its properties? Free electron. This is for graphite, by the way, not for diamond. Carries an electrical charge. Yes, well done, Alicia. So that makes it a good conductor of electricity. All right. So the 4th electron that is not used for bonding is delocalized. So that was what I was just talking about now. So that means it is a good conductor of electricity as its delocalized electrons can carry a charge. Yeah, thank you, Andrew. So that's a unique property about it. Another unique property about it is that it is soft. The reason why it's soft is because remember it's got this layered structure. So these layers can slide. Look at it to the side. These layers basically look like this. So one block of graphite would look like this, and these layers can like slide over each other, and that's what makes it like a soft sort of substance. So for that reason, it's used as a lubricant. Because the layers can slide over each other. Okay. The next one is very similar. Okay, so this is graphite. Who knows what this one's called? 1 layer of graphite. What's 1 layer of graphite called? So it's a single layer of graphite and it is strong and light. Graphene. Yes, it is. Just careful with the spelling, Andrew. It is graphene with an E. Graphene. So just like graphite, it's a good conductor of electricity because remember what I said, because it forms 3 bonds, there's that delocalized electrons which can carry a charge. So it's a good conductor of electricity. Due to its delocalized electrons. So it's used in electronics. Okay, that's graphene. Next one, we've got this one, which is spherical. Anyone know what this is called? So the general term is fullerenes, but this one, which is a circular one, what's this one called? It's a really long word. You need to know the name of it, and you also need to know the molecular formula of it. It says down here, actually, C60. What is it called? Aaron's got it. Buckminster fullerene. Okay, so fullerene is the general term for it. It's an example of a fullerene. This is another example of a fullerene. This specific one, the one that looks like a football, is Buckminster fullerene. And it's a spherical fullerene. So it's a sphere with a formula of C60. So one molecule of this has 6 together. And some of them are hexagons, some of them are pentagons. It literally looks like a football. So the good thing about these fullerenes is that they have these hollow shapes. So one's a sphere. This other one here is a tube. Yeah, they're hollow. So inside you can carry stuff within it. It's useful for as a catalyst and as a drug delivery. So to deliver medicine into the body. So that's what it says here. The structure of the rings is based on hexagonal rings of carbon atoms, but they may also contain rings with 5 or 7 carbon atoms. They can encapsulate. So that basically means they can cover other molecules. So like if you wanted to transfer like some sort of medicine or drug, you can encapsulate in the middle of this ball and then you can deliver it into the body. So that's what makes them quite useful for that stuff. So they can encapsulate the other molecules and are used as industrial catalysts. Is that whole sphere one molecule, Militia asked? Yes, it is. Yeah, one molecule. So it's a lot of these molecules. If you have a sample of it, it's going to have loads of these molecules. Okay, and then the last one is nanotubes. Again, it's another type of fullerene, but these ones are cylindrical. Cylindrical fullerenes with have a very high length. So they're quite long. They have high length to diameter ratios. They're used for nanotechnology, for electronics and materials. They're good conductors of heat and electricity. And the reason for that is, again, you've got this hexagonal shape, just like graphite. They form 3 carbon bonds, so they have a delocalized electron. Yeah, so they have delocalized electrons. Meaning they can be used in electronics again. And nanotechnology. What's very unique about them is they're very strong and they're not very heavy. So they have high tensile strength. That's like the scientific way of saying they're strong. High tensile strength without much mass. So you use them in things like tennis rackets because you want those to be quite light, but at the same time you want them to be quite strong as well. You don't want them to break when you hit the ball, right? So they're used in tennis rackets as well. Okay, that's quite a lot of information, guys. Thanks for listening. Let's we've got about 5 minutes left? Yeah, 5 minutes left. Let's just try some quick questions. Okay, so this one here, see, I told you that they could ask you about 3D models. All you have to do about 3D with 3D models is literally count up the different atoms we've got. So you see here, the white ones are the chlorine atoms. The dark gray ones are oxygen atoms, and it's asking to figure out the molecular formula. What would you guys say the molecular formula is this is for this one? So we've got chlorine here, then we've got oxygen 1, 2, 3, 4. La 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 la. What would you guys say the molecular formula of this molecule is? Let me know in the chat. Andrew says C2O7. Yep. You said C2 actually. It's not carbon, it's chlorine. So it's actually going to be Cl2O7. You're close. Cl2O7 because it's chlorine. Yeah, Militia made the same mistake. So be careful. I think this caught people out in the exam actually, because loads of people put carbon because it's normal to have carbon, right? It's like an organic molecule. So I do think loads of people made this mistake. Here's another one. Okay, try this one now. Tell me what you guys think the molecular formula of this one is. This one does have carbon. So carbon bonded to 3 white ones. The white ones are hydrogen and 1 oxygen. So put that all together, put the numbers together. COH4, CH4O, both saying the same thing. They're both correct. Yeah. We got 1 carbon here. We got 1 oxygen here, and the others are hydrogens. 1, 2, 3, 4 hydrogens. Yeah, looks like everyone's saying the right answer. Oh, Leona, I didn't even see you the whole lesson. I hope you come on right at the end. CH4O. CH4O. Well done, guys. CH4O. Let's see what else we've got. Here, what type of structure is silicon dioxide? Real quick one, guys. A, B, or C? Yep. Giant covalent. All the atoms are bonded with strong covalent bonds. So it's A. Why does silicon dioxide have a very high melting point? Okay. What would you guys say the answer for this is? You got to be very careful here. Actually, yeah, no. They haven't tried to trick you here. Would you guys say it's A, B, C, D, or E? Any answers? Why does it have a high melting point? So high melting point means it's going to be hard to break those bonds, right? What type of bonds are we dealing with here? No one knows. C and A. People are saying C and A. It has a giant structure. It has strong covalent bonds. Okay, everyone's going with C and A. Yes, it's a giant structure. Has strong covalent bonds. Look at that. That's a giant structure. Every single atom is held together with a strong covalent bond. So it's going to take a lot of energy to break. All right, guys. I think I'm going to leave it there. Let me know if there's any questions before I shoot off. And yeah, so next week we'll be doing a bit of physics and biology. Is it biology? Yeah, biology and physics. I think physics is circuits, electricity. and biology is diseases. So yeah, that's what we'll be doing next week. So same thing again, be at 5 p.m. next Sunday. No worries, guys. Have a good evening, and I'll see you guys next week. Take care.